Hello, my name is Han Tran, and in this video we're going to be continuing a problem that we began in a previous video. In the previous video, we laid out the problem that dealt with a continuously stirred tank reactor, and we looked at the parameters that we were given, and then we derived some differential equations that showed the change in concentration in the tank over a change in time and the change in temperature of the tank over a change in time. And so what we're going to be doing in this video is we're going to be reviewing all that information, but then we're going to be using all that information to code out a script that will allow us to graphically plot the change in concentration over change in time and the change in temperature over change in time. So let's begin. We're going to start by taking a look at the information that we covered in the previous video. So here's the problem that we looked at, and it tells us how we have a CSTR, and it tells us about the coolant temperature and how it's in positive and negative directions. It also tells us that there is an exothermic first order reaction from A to B, and it gives us just the temperature, the concentration, and then it gives us a bunch of parameters, and it says two cases should be simulated. One by changing the coolant temperature from 300 to 290, and one by changing the coolant temperature from 300 to 305. And so what we did was we wrote out all of the parameters and what the parameters told us. So we had the flow rate given to us, the concentration in the tank, the initial concentration, the temperature of the tank, initial coolant temperature, initial tank temperature, volume, density, heat capacity, enthalpy of the reaction, activation energy over a gas constant R, and a constant of the Arrhenius equation, and then also the heat transfer constant. And we used all that information to write out our two differential equations here. And so we're going to use all this information, and we're going to head on over to Collaboratory. First thing that we're going to do is we're going to import some packs that will allow us to use function packs like e to the negative activation energy divided by gas constant R times temperature. That's the Arrhenius equation. So we're going to use mathematical functions such as e, so we need to import packs for that. We also need to import packs to solve the differential equations that will allow us to figure out what the concentration at a given time and the temperature at a given time is. Additionally, we need to import packs that will allow us to graphically plot the simulation. So those three are the packs that we're going to import. So the one for the mathematical functions is numpy. So we're going to import numpy, N-U-M-P-Y as NP. We also want to import from the scipy.integrate. We are going to import solve IVP, and this is going to allow us to solve a function for a set amount of time with initial conditions. And then from plotly, P-L-O-T-L-Y dot subplots, we are going to import make underscore subplots. So this is going to allow us to plot our simulation. And so the first thing we're going to do is we are given all these parameters. So what we want to do is first input that into our code. So we have the flow rate, which is 100. This is liters per minute. We also have our concentration going into the tank, and that is 1 mole per liter. We also have our initial concentration, and that is 0.5 moles per liter. And then we have our temperature going into the tank, and that is 350 Kelvin. And then we have our volume, which is 100 liters. We want to make sure that this is an equal sign because we are defining the temperature going in. And then we also have the rho, which is our density. So that is 1,000 grams per liter. And then we also have our heat capacity, which is 0.239 joules per gram Kelvin. And then we have our enthalpy of reaction, and that is 5 times 10 to the 4th joules per mole. And then we also have our activation energy. That is 8,750 Kelvin. And then we have our constant for the Arrhenius equation, and that is 7.2 times 10 to the 10th. And that is minutes to the -1. And then we have our heat transfer constant, and that is 5 times 10 to the 4th joules per minute Kelvin. And then we also have our initial temperature, and that is 350 Kelvin. And then we also have our temperature of our coolant, which is 300 Kelvin. And that is all of our parameters. And so we're going to shift enter, make sure everything is written out correctly. And so now we can begin writing out the function that we're going to be using to solve for the concentration and temperature. And so we need to define the function. And so we're going to define the function, and we will call it the right-hand side, because what we'll be doing is we will be wanting it to return the right-hand sides of these equations. And then what that's going to do is we're going to use that and plug it into solve IVP, which will solve for the differential. It's solving for the integrals. And so what we're going to do is we are going to want to define it by giving it first an independent variable. And so in that case for us, it's going to be time. So we are going to be inputting the time. So we'll call that T. And in this case, we're solving for two things. We're solving for the concentration and the temperature. So we're going to put that in as vector, VEC, and then we're going to define what that vector is. So that vector is going to solve for the concentration, and it's going to solve for the temperature. And so now what we're going to do is we're going to input these equations that we wrote here. And so that's what we wanted to return. We wanted to return the right-hand side of these equations. And so the first one for concentration, it is going to be flow rate divided by volume multiplied by the concentration going in minus the concentration in the tank minus the reaction rate multiplied by the concentration in the tank. And that is the first differential equation. But since we're doing 2, it's going to return it as an array. And so we want to make sure we use square brackets. And then so the second equation, which will be the second term in this array, is going to be the flow rate divided by the volume multiplied by the temperature going in minus the temperature in the tank plus the negative enthalpy of reaction multiplied by the reaction rate multiplied by the concentration in the tank divided by the density multiplied by the heat capacity, and we are going to subtract the heat transfer constant multiplied by the temperature in the tank minus the temperature of the coolant, and that is all going to be divided over the density multiplied by the volume multiplied by the heat capacity. And then, so when we look at this equation, we can see that we have one thing undefined, and that is the reaction rate. And as we can see here, there's squigglies under them, which means we have not defined them. So let's go ahead and define the reaction rate. When we were talking about parameters in the previous video, we said that the reaction rate is Arrhenius equation, so that's going to be the constant K naught multiplied by numpy NP, and we're going to do EXP. This is the E value, and it is the negative activation energy divided by the temperature. So now that that all looks to check out, we're going to expand our code here, and what we're going to do now is we're going to do solve_IVP, and what solve_IVP does is it solves a system of ordinary differential equations if we give in independent variables such as the time, so this is a set time, as well as initial values. It's going to require both of those, and then it's going to use the function that we give it, and it's going to solve the differential equations system that we provide. And so we're going to do just that. So we're going to do solve IVP. The first thing that solve IVP needs is a function. So that is the function we defined above, which we named RHS, right hand side. And what it needs is the independent factor, that is time. And so we need to determine how long we want the time to go for. So let's say we want the time to go for 100 minutes. So it's going to go from 0 until the time that we set above, and we need to provide initial values. And so here we have two initial values. We have the initial concentration and the initial temperature. So we're going to put in the initial concentration and the initial temperature as our initial conditions. And then what we're going to do is we're going to do method equals rado. This is a way of solving ordinary differential equations. It's one of the methods that can be used. There's many methods, but this is the method that we will be using for this specific code. And then dense underscore output equals true. So what this does is it continuously solves the differential equation. So if we shift enter, we have to shift enter from the top. If we shift enter, we have all this information. What we care about is the solution, so SOL, and we will name it SOL, so we're shift enter. And so now what we can do is we can begin plotting this simulation. And so The first thing we're going to do is we are going to create numbers for it to plot. So we want to create a series of time values that it will plug into this equation to find the concentration and the temperature. And so we're going to give it times for the plot, so t plots, and we're going to use numpy.linspace. So what np.linspace does is it's going to have you input an initial value, so the starting value, the ending value, and the number of values in between, and it's going to linearly space it based on that. And so we will have it start at 0, go to the end of the time that we set above, and have, let's say, 500 steps. And then we want the solve by VP to solve for these values. So we want the solve of the t-plot, and that's going to get output two things. That's going to output the concentration first, because up here, as you can see, we have concentration first, and then it's going to output the temperature. So now that we have that defined, we're going to shift enter, and now we can plot our simulation. So the first thing we're going to do is we're going to make a subplot. So we're going to name it fig equals subplot make underscore subplots. And for this subplot, we're going to have 2 columns and 1 row. And so it will plot the concentration on one side and the temperature on the other. And then now we can add to our subplots. So we're going to do fig, which is the name of our figure, dot add underscore scatter. And the x value is going to be t plot, which is the times that we have set. So that's going to be on the x-axis, and then on the y-axis is going to be the concentration of A. And then our mode is going to be lines. And we are going to have this be on the left side. So that's going to be the first column, the first row, or the only row. And we will name this concentration of A. And then we also need to add another figure. So our name of our figure is fig.add underscore scatter. So our x-axis is still going to be the time. Our y-axis now is going to be the temperature. And then our mode is still going to be lines. So it's going to be plotting one consecutive line rather than a bunch of small markers. This is now going to be in the second column, so it's going to be on the right. It's going to be in the only row, the first row. And we will name this tank or temperature of tank. Shift enter. And so now here we have our plots. And if we take a look back at the initial problem that we were given, it wants us to have the simulations by changing the coolant temperature from 300 to 290 and then from 300 to 305. So right now it's at 300, and what we're going to actually do is just to condense our plots a little bit and to kind of almost zoom in. We're going to make the time just 10 minutes rather than 100 minutes. Okay, so now we can see the plot, and this is it at 300 degrees, or 300 Kelvin. And so what we want to do is change the temperature to 290. See how that affects our simulation. And then we can also change the coolant temperature to 310. And as we can see, that actually causes our simulation to oscillate quite a bit, and then it'll reach eventually a steady state. So now that we have our simulation and we know that the simulation works, let's take a minute just to analyze what's going on here. So we'll start at the lowest temperature in the problem, which is 290 Kelvin. And so what we see here is, on the right here we have the temperature of the tank. So we decreased the temperature of the coolant. So now that the coolant is cooler, that's going to decrease the temperature of the tank. So we can see that here as it decreases till it reaches a steady state around 312. And so as the temperature of the tank decreases, the reaction rate is also going to decrease. And since the reaction rate is decreasing, since the reaction is going from material A to B, what's happening is less of A is being consumed, so the concentration of A is increasing. So let's now move on to our middle temperature in the problem, which is 300 Kelvin. So here we can see the temperature in comparison to the 290 Kelvin of the coolant. It takes a little longer to decrease. It has kind of a less of a sharp increase or decrease because the coolant is not as cold, and then additionally it reaches steady state around 324 Kelvin, which with 290 coolant it was around 312. So the steady state temperature is of course a little more as well, and similar, the same thing happens here. It just happens a little later because it takes longer for the tank to cool, but the temperature cools down. Over here it begins cooling, let's say around 2 minutes. Same thing over here, around 2 minutes it begins to increase in concentration because the temperature is beginning to cool, which means less of A is being consumed, which means the temperature of A is increasing. So we have that at 300 Kelvin. Now if we go up to 310 Kelvin, which is the highest temperature in the problem that we were given, we can see we have actually somewhat of an oscillation here. And so since the coolant is at a greater temperature, the tank will get hotter, the reactor gets hotter, because the coolant is a greater temperature, so it's not cooling the tank as much. And because the tank is getting hotter, what's happening is as the tank continues to get warmer, more and more of the A material is being consumed and it's going into this reaction, and so the concentration is rapidly decreasing because what happens is as the temperature increases, the reaction is going faster and faster, and so more is being consumed than is there, and so the concentration is decreasing, or more is being consumed than is coming in, so the concentration is decreasing, and so we have it continue to get warmer, continue to speed up, continue to consume more, decrease in concentration, and then continue to get warmer, continue to increase in reaction rate, continue to consume more, and continue to decrease in overall concentration. And so we can see that here up until about, I would say, 0.4 minutes, same thing over here. Around there, it then suddenly cools really quickly because it's reached that temperature, and now it begins to cool because of the coolant. And so as the tank begins to cool, it's kind of the opposite reaction. The reaction rate begins to slow down again, and it begins to slow down again, and so the concentration in the tank increases because the reaction is slowing down, so not as much is being consumed. And then because of that, what happens is there begins to be more of A, so the reaction begins to increase again, and the temperature begins to increase, and so more is being consumed, and it kind of does this oscillation until it eventually reaches its steady state over here on the right. If we were to look at other temperatures, like if we were to look at 305, Because here we can see that eventually it'll reach a steady state. If we were to look at, let's say, 305, what actually happens is there is continued oscillation. It's kind of the same process, but there's a continued oscillation, and we don't ever see, at least in this simulation, if it reaches a steady state. We can also see here it can be very dangerous when this occurs because the reactor can get very hot, and so it can easily cause explosions, and that is not good. And so when we look at these simulations, it can tell us a lot about how the reactor will behave, what is safe, what is not safe, and which is why these simulations are so important when we're looking at them. And we can change and see what coolant temperature would be best for the reaction and for what is needed. And so as we adjust, we can continue to see the simulation. Another thing we can notice about the simulation is they're almost mirrored over the x-axis here, and if we change the temperature, that kind of mirror continues to be seen, and that's because as the temperature decreases, the concentration is going to increase. They're inversely proportional, and so we can see that in the simulations. And so that is the reactor dynamics of a continuously stirred tank reactor, and it's the simulation for the concentration and temperature